This series again is one of the known ones. Now we don't again if we even if we don't know what this series is, we're still going to test it, and we're going to find the radius from using the ratio test. So I'm going to first of all set up the ratio test. Limit as n goes to infinity of our n plus 1. So our n plus 1 is going to be -1 to the power n plus 2, x to the power 2n plus 2, and in the denominator we end up with n plus 1 minus 1 just gives us n squared. So there's our n plus 1, and that's divided by our n. So we end up with x to the power 2n divided by n minus 1 squared. Okay, and then we're going to then take the absolute value of that. We can group a few terms to make this simpler to evaluate. So as n goes to infinity, we're going to group these terms together. So that just becomes -1. So we have -1 as one of our factors. We'll group together our x terms, these x terms. We'll do that in blue. So we end up with x to the power 2n plus 2. So I'm going to write this as 2n times x squared. And in the denominator, we have 2n. Okay, so that's going to be grouped together. And then we're going to group together our n terms. So we end up with n minus 1 squared over n squared. And that's going to get grouped together. Okay, so some things are going to cancel out. So these are going to cancel out here. So we end up with x squared. The n minus 1 over n squared, that's going to have a limit of 1. Okay, so we'll simplify this expression. Limit as n approaches infinity. We have the -1, which really is not significant. Okay, we have this x squared term. And we're going to be able to simplify this n minus 1 over n all squared. That's just going to end up being 1, or 1 squared. Okay, so when we evaluate this limit, we have the absolute value of the x squared times 1, and we do have that extra negative in there, but that extra negative really becomes not significant because of the absolute value here. And we need that to be less than 1. So we end up with x squared is less than 1, which we can translate into x is less than 1 and x is greater than -1. Okay, so we have our center. This represents our center, c equals 0. We have our radius. Okay, your radius is equal to 1, 1 to the left, 1 to the right, and then we can test our endpoints. So we're going to test x equals -1. So we substitute into our series n equals 0 to infinity. We had our original -1 to the power n plus 1. We replace the x with -1 to the power 2n. So since that's an even power, that's always going to be positive. And we end up with n minus 1 squared. Okay, so this, if I simplify this, we have an alternating series here, n plus 1 to negative. That 1 just becomes -1 to an even power becomes 1. And then we have n minus 1 squared. Now that is a p-series of power 2, so this is convergent. P is greater than 2. Okay, so then we're going to include this endpoint of -1 as part of our interval. We can then move on to the other side. When x is equal to 1, my series then looks like this: n equals 0 to infinity, -1 to the n plus 1, and we get 1 to the power 2n. Okay, so that's going to be always just 1 anyways, and we end up with n minus 1 squared. Okay, I can simplify this a little bit, but essentially this is the same thing. It is an alternating, but it's p series greater than 2, so this converges absolutely. Okay, we don't even have to worry about that -1, although that -1 will help this converge. It converges absolutely because it's a p series with p greater than 1. Okay, oops, I wrote here and here. P should be greater than 1. And the same thing here. This is convergent because a p is greater than 1. Our power here is greater than 1. Okay, so then we include this endpoint here. So we have our center at 0, radius of 1, and our interval is from -1 closed to +1 closed. So it's a closed interval on both sides from -1 to +1.